second, third. Yeah, they can always switch later if they get the wrong one.
Is it working? We'll see.
That's a little better.
Okay. Good morning, and welcome to our third plenary session. As president of the Geochemical Society, it's my pleasure to begin today's session by presenting the Society's medals, which recognize some of the most excellent scientists in our field. First, the F.W. Clark Award is given to an early career scientist for a single outstanding contribution to geochemistry or cosmochemistry, published either as a single paper or as a series of papers on a single topic. This medal is named for Frank Wigglesworth Clark, a chemist who lived from 1847 to 1931 and who did pioneering work to explain the chemical composition of the Earth's crust. This year, the medal is presented to Francis M. McCubbin, astromaterials curator in the NASA Johnson Space Center, in the Astromaterials Research and Exploration Science Division. Dr. McCubbin is recognized for his work on water and apatite that changed our understanding of volatiles in the moon. His nominator described him as respectful in disagreement, brilliant in thought, thorough in experiment, and diligent in expression. We are very pleased to honor this bright young scientist and look forward to his future discoveries. Please join me in congratulating Francis McCubbin on receiving the 2017 F.W. Clark Award. Okay. Next, we have the Claire C. Patterson Award, recognizing an innovative breakthrough of fundamental significance in environmental geochemistry, particularly in service of society, consisting of either a single outstanding contribution or a short series of papers published within the last decade. Claire Patterson had a remarkable career, during which he developed the uranium-lead dating method. Using lead and uranium isotopic data from the Canyon Diablo meteorite, he calculated an age for the Earth of 4.5 billion years, a figure far more accurate than those that existed at the time, and one that has remained unchanged for over 50 years. He also played a major role in raising awareness of the dangers of lead contamination in the environment. This year's recipient of the medal, named in his honor, is Kai Hinrichs, Professor of Organic Geochemistry in the Department of Geosciences, Marum, at the University of Bremen. Professor Hinrichs is recognized for his work on the interactions between microbial life and the carbon cycle on a range of spatial, temporal, and molecular scales. His far-sighted approach to scientific research has led to deep understanding of the functional relationships between the structures of membrane polar lipids and the ability for some microbes, and particularly the archaea, to survive for millions of years in the desert environment of the marine subsurface. This knowledge has had impacts well beyond the initial objectives of individual papers. For these achievements, I'm pleased to present him with the 2016 Claire Patterson Award. Finally, the Geochemical Society's highest honor is named for Victor Moritz Goldschmidt, who is considered to be the founder of our field. His classification of the behavior of the elements of the Earth and meteorites has laid the basis of modern geochemistry. The Goldschmidt Medal recognizes major achievements in geochemistry or cosmochemistry, consisting of either a single outstanding contribution or a series of publications that have had great influence on the discipline. This year, the award goes to Jill Banfield, professor in the Department of Earth and Planetary Science at the University of California, Berkeley. Professor Banfield studies the structure, metabolic potential, and functioning of natural microbial communities in sediments, soil, water, biofilms, and animals. She develops and applies new methods in molecular geomicrobiology and microbial ecology. She also studies nanoparticle formation and the behavior of nanoparticles and clay minerals in the natural environment, also called nanogeoscience. The astounding breadth and impact of her work is well reflected in her remarkable citation record, and also even more so in the tremendous amount which her work is appreciated. As Victor Goldschmidt's impact on geochemistry is still felt more than a century after his career began, I'm certain that Professor Banfield's contributions to her varied fields will continue to inspire other scientists for a long, long time. Please join me in congratulating Professor Jill Banfield as she receives the 2017 VM Goldsmith Award. I'd also like to remind you about a special event taking place this evening. Do we have a slide for that? This is in honor of Jerry Wasserberg, who is, of course, one of the great giants of our field who passed away last year. It's described as A Lunatic's Life, the Isotopic Adventures of G.J. Wasserberg, and it will take place at 5:30 in Salle 252 AB. Friends and colleagues of Jerry Wasserberg will share stories about his remarkable career, and everyone is invited to come and enjoy the short talks and reception. I strongly encourage you to do so. Okay. Thank you for your attention. I'd now like to introduce Professor Hisayoshi Yorimoto, President of the Geochemical Society of Japan, to present the Geochemical Journal Award.
Okay, next is the Geochemical Journal Award. The Geochemical Journal Award is bestowed annually by our society for the most outstanding paper published in Geochemical Journal in the previous year. This year, the recipient is Dr. Hidenori Genda of Tokyo Institute of Technology. The paper title is Origin of Earth's Oceans, an assessment of the total amount, history, and supply of the water. It is my great pleasure to introduce Dr. Hidenori Genda for the Geochemical Journal Award of this year. Congratulations.
Good morning, everyone. I am delighted to introduce Dr. Hélène Langevin-Joliot for today's conference. Dr. Langevin-Joliot is Emeritus Director of Research at the National Center of Scientific Research. She graduated from the prestigious École de Physique and de Chimie Industrielle de la Ville de Paris, and she obtained a state doctorate in nuclear physics. She is a renowned scientist, notably for her work on nuclear reaction at moderate energy and on the movement of nucleons at high excitation states. She contributed to the creation of the Institute of Nuclear Physics in Orsay, where she was in charge of the Department of Research. She is also very active in several areas of research, including the preservation of the scientific heritage, the status of women in science, and the international peace movement. You may know some members of Dr. Langevin-Joliot's family. She's indeed the daughter of Frédéric and Hélène Joliot-Curie, who, among other things, discovered the artificial radioactivity. And she's the granddaughter of Pierre and Marie Curie, and her family totalized not less than 6 Nobel Prizes. If I am correct. So today, Dr. Hélène Langevin-Joliot will present us some aspects of the life and achievements of her grandparents. Please join me in welcoming Dr. Langevin-Joliot. We need a script.
Oui, j'avais un bon paquet de papier. Okay.
Laurie, please.
Thank you so much.
She stole them.
Okay, no problem. So, maybe.
Elle va s'occuper des slides.
Okay. Ah. Qu'est-ce qui se passe là? On peut passer le. So there is something missing. Okay, and take that out. So, I will try to describe maybe part of the work of my grandparents and try also to speak about radioactivity in their time. In fact, a scientific revolution occurred at the end of the 19th century, which changed the scope of science. After that, the microscopic level was experimented, and not only the microscopic one. Okay, in 1895, X-rays were discovered by William Conrad Röntgen, and this was something which created an event not only in the scientific community, but for the public, with the first radiography of the hand of Mrs. Röntgen. 2 years later, Thomson, studying cathode rays, measured the charge over mass ratio. And it was a coordination of many works before. As you know, cathode rays became electrons. In fact, the uranic rays discovered by Henri Becquerel in 1896 were just noticed by few physicists. 2 years later, the discovery of polonium and radium by Pierre and Marie Curie changed the situation and what the uranic ray became the discovery of radioactivity. The name radioactivity was given by Marie. And this study became very important in the future. Radioactivity, I will not speak about that, has opened the way to atomic physics, then to nuclear physics, had opened the way to nuclear energy and many applications, and many consequences in other disciplines as astrophysics, geophysics, and geochemistry, and biology also. Marie Curie was 31 years old, and Pierre Curie 39 when they discovered radium. He was already a well-known physicist, in spite of occupying a very modest position. She has no position whatever. It is difficult to imagine more contrasting personalities than the personality of Pierre and the personality of Marie. In fact, this helps them to have a very good collaboration. Also, yes, it's many times like that. And this complement, they share, on the other hand, many common ideas about family and about societies. They were married in July 1895. Pierre, on the left of this picture, his dreamy mind is quite obvious. He is here with his brother and his parents. It was at the time, 1880 approximately, where he was working, discovering piezoelectricity in crystal quartz and studying that with his brother. Then he was appointed at the School for Chemistry and Physics operated by the city of Paris, a very modest school at that time. He worked at that time full-time for teaching, saved some hours for research, and spent nearly 15 years developing the idea of symmetry from crystal to the situation in physics, studying the symmetry conditions for electric field, magnetic field. Okay, something very important at that time, but not recognized and so important in modern science. When he found some time, it was allowed to start experimental research again. His subject for it was quite different. He studied the dependence of magnetic property with temperature. In fact, he found, as expected, that diamagnetic and paramagnetic elements don't behave the same way. And studying this element, all elements on a large range of temperature, he discovered that ferromagnetic one turned to paramagnetic at a higher beyond what is known at the Curie point. The story of Maria Sklodowska, a young Polish girl going to Paris to study mathematics and physics, is well known in a sense. Many people have heard about. She is shown here at 17 with her elder sister, Donia. And I think here you have a very absolute, very resolute character on this picture of the two sisters. They combined their efforts to be able to go to Paris because it was not allowed for women to study at the University of Warsaw at that time. She has a job of governess for children for several years to help her sister going to Paris and studying medicine. Then she could go to Paris with the help of Borgonia. She registered at the Sorbonne in Paris in 1891. Marie Sklodowska. In the time, during the 3 years after, she passed very brilliantly the exam on physics and mathematics. And it happens that she received some I would say, Oui, bon. Yes, a paid commission, exactly that, a paid commission. It was not often at that time, but paid commission. And it was the occasion of a Polish professor to invite Pierre Curie to help Anne-Marie together at home. They find them, okay, interesting one and the other. To tell the truth, both of them at that time have ruled out love and marriage for their life program. And Pierre changed his mind within 2 days or 3. Okay, Marie saw to that nearly a year. For her, she was convinced that her duty was to come back and live with her family in Poland and teach there. If you read a few letters written by Pierre Curie during Marie's vacation in Poland, they are both, how to say, romantic and arguing to try to convince her to come back. It will be a fine thing to live together, hypnotized by our dreams, your patriotic dream, or humanitarian dream, and our scientific dream. Marie chose Pierre and the scientific dream. This is a photography taken at the time of their weddings. And there you see them set off with a bicycle, a well-given, a gift for their weddings. My mother, Hélène, was born 2 years later in September 1897. At the time, Marie decided not to try to teach it, to get a teaching position in France, but to undertake a thesis and turn to research. And the subject was those uranic rays from Becquerel's ray, weak Becquerel ray from radium, but which was a spontaneous emission. They find that very interesting, and it was, in fact. I show here, it was for an exhibition, the presentation, the original apparatus of Pierre and Marie Curie. At the right, you see a very crude ionization chamber, the 2 plates and the salt to be studied was put on the lower plate, a high voltage, 100 volt voltage between the 2 plates. You see the shielding here. At the left, a piezoelectric quartz, which comes from the work of Jacques and Pierre Curie nearly 15 years before. As it is well known, when you exert a traction on the quartz, you produce a certain amount of charge. And the connection, which are not shown here, to the electrometer, which is here in the center, were such that the ionization current can be exactly compensated during a certain time by the current from the quartz if you tracked it and finished that. With that, they were able to measure charge as low as 10 to minus 11, which was very, very small at the time. In fact, Marie decided to start our study by developing quantitative measurement on uranium and the salt of uranium to prove that indeed, as suggested by Becquerel, the spontaneous radiation of uranium was indeed an atomic property. And she obtained the result very quickly. The possibility of a similar emission by other elements was an open question. Marie selected a number of elements that are measured and measured. The search was not so successful. Only thorium was emitted a spontaneous radiation at the time. In fact, the idea to come back to the minerals of uranium, pitchblende in particular. So it was a problem because when she measured pitchblende, she found it gave more radiation than normal for its uranium content, which was known. She checked the apparatus again and again, and finally that was true. So following idea was taking another mineral, chalcolite, maybe I don't use the right name, was a much simpler mineral with uranium. So she take laboratory things, and she managed to get an artificial chalcolite, which finally was completely normal, completely different of the chalcolite from the mineral. She finds the result strong enough to publish at a note at the French Academy of Science with the strong conclusion the minerals may contain an element much more active than uranium. The statement opened new research, a new research field, and Marie and Pierre, Curie, decided to work together from then on. You see them with the electrometric setup, and Marie is just looking at the equilibrium between the two currents, and she is handling the weight that is used for the traction. In fact, you can calculate today that they work with 120 grams of pitchblende. And in that, you have about 30 milligrams of radium and 9 nanograms of polonium. They quickly convinced themselves that, okay, analytical chemistry was not enough, that it was needed, and it was a new method to use the emission of radiation to follow what happens along the chemical attempts they made to find the new element. In fact, it was a beginning for radiochemistry. Not exactly now, but no, I'm searching. These are the piece of the notes they took for the discovery of radium. And in fact, it was not a chemist and a physicist. In fact, the two of them performed chemical treatment, and the two of them perform measurement of activity. At the left, Pierre Curie, at the right, Marie. In July 1898, they discovered polonium. In fact, there was a very small amount of polonium in the sample, which already have a high radiation level. It followed bismuth, more or less. And they published a note. In December, radium was discovered with the collaboration of the chemist Gustav Bémont. And in that case, in spite of being very tiny, the amount of radium was enough so that a specialist, de Marseille, could observe a new spectral line. This was a strong proof of the element for physicists, not sufficient for chemists. Okay. One remark I would say, already just a few months after, Marie speculated that the radiation is an emission of matter, while at the same time the radioactive substance lose weight. A materialist theory following our expression, alternative to the possibility, which was discussed at that time, that radioactive substances borrow from an external radiation the energy they release, or that even thermodynamic laws could fail at the microscopic level. The new discipline developed rapidly on this subject with many chemists and many physicists interested in, and it expanded many directions. Speculative idea led place to experimentation. I just mentioned in this beginning the nature of radiation. The starting point was the work of Rutherford on the slowing down of the radiation. We proved that it was complex. Uranium radiation was complex, and radium radiation was complex also, for a reason less evident at that time. Rutherford had called the very absorbable radiation, it had called it alpha rays, and the other one, more penetrating, beta rays. This use was for many, many years, and now gamma rays were discovered by Wheeler, very similar to X-rays, but more energetic. In fact, about this radiation, attempts were made to know what was alpha rays and beta rays. For beta rays, studies of deviation in magnetic field proved rather rapidly that they were negatively charged, and somewhat later that they were electrons. In the case of alpha rays, no deviation at the beginning, and after a lot of time, Rutherford again find they were positively deviate, and a lot of work, several years, with magnetic field and electric field, finally proved that alpha rays was an atom, an helium atom with two positive charge. This was something very important. It's matter. Prove it was matter. And in this matter, helium was very important for physicists and for chemists, but also for geologists, which immediately they know before, but they search for uranium minerals again and found helium in all minerals they check, either uranium, either thorium. Another very important point was the property of radioactivity. Among them, something which seems to us obvious now, was the idea that no chemical agency, no physical agency temperature, pressure change with chemical reaction, nothing changed radioactivity. Marie Curie spent the time for her thesis by studying that in details. The Curie, more generally, were interested in other property which could be, in particular, used for application. Electrical properties were known, but it happens that Pierre Curie let a piece of radium, very small amount, but nevertheless on his arm, and studied the evolution of the wound. This was the beginning of a collaboration with physicians who, at that time, physicians start to use radium for the treatment of lupus, then of cancer. And you know that 20 years later, that turned to effective radiotherapy, most important one. Oui. In fact, from the beginning, the link between radioactive substances and chemical elements was one of the main problems. The first step was to consider that, okay, the radioactive substance like uranium, thorium, then radium, after the fact that Marie measures the atomic weight, all that was chemical element because the radioactivity was constant. Radioactivity being constant, okay, they may be chemical elements. And in addition, new radioelements like actinium, but a so-called ionium and mesothorium and so on. Others, okay, radioactivity was constant. They were tentative chemical elements. But other radioactive substance seems to decay, more or less. It was very complicated. It seems that some of them have the radioactivity increasing. Rutherford studied especially what was called the emanation of thorium, and later the emanation of radium. And at the end of those experiments, they conclude on what is written here, and was the main conclusion for radioactivity for many years. Radioactivity is a transformation of a chemical element into another one by emission of radiation. Their transformation theory, it was called like that, put order in an impressive number of complicated facts. Some order begin to be given to the situation. It was also understood that radioactivity was a phenomenon at random with the many consequences, the statistical law, and so on. In fact, I come back to Marie and Pierre. Marie has her thesis to prepare, and for it, the question was to perform the separation of a pure radium salt to be able to have the atomic mass. The only place they have found for that was at the left, this shed. And the shed have really no equipment for chemistry. It was really a very complicated situation. And in fact, especially because they were working with radioactivity and with not 4 tons. It is the legend of the Curie with 4 tons of pigment is not, it's a legend. In fact, they organized the first step of the treatment outside and give it to others. But they have to perform all the crucial operation of chemistry for 10, 20, and more dozen kilograms of the mixture they were handling to try to separate clearly radium chloride from barium chloride. You see at the right, you see them in that same lab. They are looking at some, how to say, the final operation, fractional crystallization of the 2 salts many times, until, the radium chloride was pure enough to measure his atomic weight. In a letter to her sister, Marie described her killing work. But you may note in several places that she also spoke of the cups of tea they drank in the shed to get warmer, and think to the radioactivity and contamination in those days. Fortunately, the Curie spent a lot of time at the lab in the evening and so on, but they also stopped working with friends. You see them here in the garden with the Jean Perrin family. They were very, very near. The 2 houses were near one of the other, and the 2 young daughters. It may be interesting to note that between the discovery of polonium in July and the discovery of radium in December, Pierre and Marie Curie just take 2 months vacation. Okay, like that. Radium, but radium I have to wait. Okay. So Curie, as general, and their friend also, love the countryside very much, the seashore also. They thought that good air, far from the town, could compensate for weariness induced by radiation. They enjoy long trips with a bicycle. I initiate my mother, even at 7, to follow them. They were very much preoccupied that the 2 daughters, they have a second one, have good health and be able in the future to be happy with sport. Marie defended her thesis in July 1897. And 3 months later, the Nobel Prize for Physics was shared by Henri Becquerel and the Curie. The story of Pierre and Marie Curie discovering radium struck the public imagination as an outstanding adventure. It was an unprecedented event that a woman played such a role in science. The attribution of the Nobel Prize was a very good thing for their material situation. But that celebrity turned to a handicap for their work. They claim about that. They were very unhappy at the end. Pierre became a professor. He became later a member of the French Academy. Okay. the love and science story of Pierre and Marie Curie stopped tragically with the death of Pierre in a street accident in April 1906. The emotion created in scientific community, scientific circle, by his death was very important. And the university in Paris took very quickly decision which clearly overcome old tradition. Marie Curie was appointed as the director of the lab. She became assistant professor, then professor 2 years later. The decision marked an important step of the way to equal access of women to research and upper level teaching activities. In fact, Marie Curie will teach radioactivity and general physics until her death for 28 years. She got a second Nobel Prize of chemistry in 1911, which recognized the importance of the determination of the atomic mass, the preparation of radium metal, the initiative of the new discipline of radiochemistry. In the meantime, her fight to obtain a modern laboratory was finally successful. The Radium Institute entered into activity after the First War. I will only comment briefly about the question discussed and developing experimentation after the transformation theory. There was a measurement of the heat emission by radium performed by Pierre Curie in the year 1903. It was not very precise problem with it, but it was a starting point, and you can compare the heat with what happened in chemical process, and the heat by radium was huge in comparison. So speculation start about the role of radioactivity inside the Earth. In fact, this new source of Earth have not been taken into account in the calculation of Lord Kelvin in old time, when he claims that the Earth was 20 million years old, and whereas the geologists and evolutionists would more prefer billion years than the calculation of Kelvin. On the other hand, if you look at the second step, one may say that the idea that radioactivity can be used at a chronometer, can be used to determine absolute age, may be taken directly from the transformation theory. But the way to radiometric dating was long and many years. In fact, there was immediately some crude estimation, which were more or less larger than those of Kelvin. Some first attempt, serious, after the discovery of isotope, some solid grounds for radiometric dating were established. and Arthur Holmes, among others, especially him. You may point pioneer work for the determination of absolute age of specific rocks. You have to wait, more than 50 years, 56, 56, for the measurement of the age of meteorites by Patterson, which approximates the age of the Earth. That is only for two reasons. One is radium, like that. Radium is one of many, many, many other radioactivities. And it has dominated the scientific work between the two, nearly until the Second War. The reason is, on the one hand, is half-life, 1,060 years. Enough so that industry can separate radium and produce for the lab, but also for industrial and medical purpose, can prepare very, very important source of radium. And those sources were very radioactive because the half-life was reasonably short, anyway. This was the first reason. The second reason for this slide is look at this number. Maybe 80 of that were known in the 1810. And it was a situation, imagine the difficulty for the chemist to try to do something with that before isotope. The isotope concept was introduced by Frederick Soddy in 1913. If you look on the straight line, it was impossible to separate what was called ionium from thorium. And this puzzled chemists and physicists, not 1 year, but more. And it turned impossible to separate what was called radium E, because all that was named radium E, radium B, radium C, radium D, radium F, which is polonium, and even radium G. Important to know if it is lead or not. So all that became possible to classify after 1913. I think I will now conclude in two steps. At the beginning of the century, when you see Pierre and Marie, they clearly claim and hope that science would benefit to all. They also, I thought, to some possible misuse of science. One can imagine that in criminal hands, radium could become very dangerous. This was a statement of Pierre Curie in the conclusion on his Nobel lecture. Today, the application of science have more than ever large consequences, good or not so good, for our society. Second point, Marie was often considered 100 years ago as just an assistant to her husband. And she is now a mythic figure, a symbol of the access of women to scientific research. Pierre Curie's role in their common work is sometimes forgotten. My last remark is about the Nobel Prize of 1903. In January 1903, an epic discussion started in the Swedish Academy because the committee for the Nobel Prize in Physics and the committee for the Nobel Prize in Chemistry both claim that radioactivity has to be taken into account in their field, not the other one. Finally, compromise occurred, and for the moment it was radioactivity will be physics. A second controversy started when only Becquerel and Pierre Curie were proposed by members of the French Academy to the Nobel Committee. Those members of the Academy had yet recognized the quality of Mary as a scientist with Academy Prize before, but a Nobel Prize for a woman. That was another thing, and they have not proposed. It happened that the well-known mathematician Gustav Mittag-Leffler was informed, and he was scandalized. And he wrote to Pierre Curie, whose answer closed the controversy. In the fall, the Nobel Foundation announced that the Physics Prize was, in fact, shared between Becquerel and Pierre and Marie Curie. This decision has been an important step for the recognition of women in science. But if you have a look on the Nobel Foundation citation on the internet, you will find that up to now, maybe I'm wrong, but approximately 5 or 6 women only have received a Nobel Prize in physics or chemistry. I think you will conclude with me that the fight for equality of women and men in science is not over. Thank you.
Est-ce que... Oh, sorry. Speaking in French. Do you have questions for Dr. Langevin-Joliot? We need a microphone, please.
And please speak slowly.
Would you like to come on stage? Oh, okay, it's coming.
Thank you. Hélène, that was a wonderful talk, very inspirational. I have a question. Your grandmother, as far as I know, was never elected to the French Academy of Science. And I don't think your mother was either. So that was a very strong statement by the academicians in France against women for many, many years, in spite of the fact that Your grandmother won 2 Nobel Prizes, your mother won a Nobel Prize. Has it changed?
More or less. It changed now. You have to say change is changing. Okay. But one remark. When Marie was not don't succeed to get against Brownlee at the Academy in 1911, the reason for which she decided never to try again, I think the reason was the campaign, xenophobe and anti-feminist, and not the question of discussing Brownlee was older than her and so on. So she was member of the Academy, of the Medicine Academy in France, because after the First War, she has worked a lot for radiography with medical people, and she was proposed to be a member of the Medicine Academy. For my mother, okay, my father was already at the Academy. And after the Second War, my mother decided, okay, why not? So she tried. She failed. And I remember very well, because this was discussed around in the family at the dinner of lunch on Sunday. She said, I will be a candidate in all cases, for free member, for chemistry, for chemistry, and maybe for, architecture or nothing. I will ask. Okay. She tried 4 times. And she failed. And she died. And the first woman in the Academy was Marguerite Perret, who was a student in the old time of Marie, then of my mother.
So if there are no other questions, this closes the plenary session, and we thank again our speaker.